If you have a sensitive soul, then you might be better off moving along. Because in this episode, you will see worlds being torn from their birthplace, others being hurled into their stars, and some simply being pulverized. We live in a time when the entire solar system seems to be in balance. Everything is immersed in an apparent calm. Sometimes, the night sky is magnified by the passage of a comet, and occasionally, an asteroid crashes into a planet. But overall, the procession of worlds orbiting the Sun gives the impression of following a well-oiled mechanism, functioning smoothly like this for billions of years. Except that in reality, when you look at the solar system, you are most likely facing a crime scene. It is believed that within it, worlds have been murdered, thrown into the Sun, or ripped from their orbits and ejected to the point of drifting alone in the cold vastness of space between the stars. Today, I'm taking you to dive into a story full of twists and turns, where the protagonists of the drama, whether victims or culprits, are always planets. Why are the planets in our solar system arranged like this and not differently? Why is Earth this far from the Sun instead of closer or farther? What mechanisms led to this remarkable arrangement? For a long time, these dizzying questions remained unsolved mysteries, until their discovery in recent decades. Thousands of other planetary systems, with their unique architectures, have put us on a path to solving them. But before going any further, I need to introduce you to our crime scene. Here you have, to scale, the planets of our solar system represented. And you can see that there are huge differences in size between the 4 rocky planets that orbit close to the Sun and the 4 gas giants, which are much more massive and imposing and are much farther away. The ice giants Uranus and Neptune are about 4 times wider than Earth and 15 times heavier, while Saturn and Jupiter weigh in at about 95 times and 320 times heavier than our planet, respectively. Obviously, the distances are not to scale, because space is so vast that it's impossible to show both the distances between these celestial bodies and their sizes in a single image without losing sight of them. To give you an idea, imagine that in a scaled-down universe where the Sun is only 10 centimeters wide, Mercury would be 4 meters away and would have a diameter about the size of a pinhead. Venus would be nearly 8 meters away, while Earth would orbit at almost 11 meters from our scaled-down Sun. And these 2 planets would be only 1 millimeter in diameter, while Mars would be more than 16 meters away. Jupiter and Saturn, the gas giants, would be 56 and 102 meters away from here, respectively. Uranus would be 206 meters away, and Neptune 323 meters beyond these distances. When we look at the peculiarities of our solar system, the first thing that stands out is that the less massive worlds orbit closer to the Sun than the much heavier ones, which are much farther away. And for a long time, people once believed other planetary systems were much like ours, with small solid planets near the star and gas giants on the outskirts. The logic is as follows. We know that stars form from huge, collapsing clouds of gas, and once they ignite, the power of their radiation pushes material to the outskirts. The lightest elements, such as gases and water vapor. And from a distance known as the snow line, this water vapor begins to freeze and then acts as a binding agent. A glue that accelerates the growth of rock and ice blocks in gas and dust disks around forming stars. And by clumping together, these building blocks will create planetary cores in just about 1 million years. Cores that are massive enough to attract hydrogen and helium from their surroundings, and thus gradually give birth to giant gas planets. While near the star, where the radiation prevents the water present in the gas disk from turning into ice. The growth of planetary embryos, which are almost exclusively made up of metals and rocks, is much slower and more laborious. Well, that's a terribly brief summary, but you get the idea. The problem with this explanation, which provides a very appealing account of the distribution of planets in our solar system, is that it has a major flaw. In fact, logic would suggest that it should be this type of configuration, with massive planets farther out and smaller ones closer to the star, which we find everywhere in the universe. However, the vast majority of the thousands of other planetary systems we've discovered over the past 3 decades have completely different architectures from one another. I'm not going to dwell on this for too long. We've already dedicated an entire video to exploring the puzzling configurations we found. I'll put the link right here. But to sum it all up for you very quickly, let's just say that the vast majority of these systems have planets that are all more or less in the same mass range and all orbit very close to their stars. We also find them in which are a bit of a mess, where planets with very different masses follow one another with no apparent logic. Others, where gas giants orbit very close to the star and the smaller planets are farther away. And in this joyful mix of possibilities, only a small portion, estimated at about 10%, seems to have some things in common with our solar system. And to have small planets near the star and larger ones farther away, the fact that so many different architectures exist has made it possible to understand why. When all the ingredients of the solar system were put into computer simulations, we rarely ended up with something that looked like our solar system. With small rocky planets close to the star and giant gas planets farther away. It wasn't really our simulations that were wrong, but rather we were the ones who were mistaken. By assuming that all planetary systems had to look like ours, and it's only with the discovery of thousands of other planetary systems that we gradually realized the cosmos is actually filled with a myriad of different mechanisms and dynamics. It's the discovery of this immense and unexpected diversity that forced us to reconsider the turbulent history of our solar system. A history during which planets that have now disappeared were very likely propelled into the sun, while others were simply torn away from their system. The first grain of sand that forced us to rethink the mechanisms of planetary system formation was the discovery of what are called hot Jupiters, gas giants hundreds of times heavier than our planet and orbiting very close to their stars. Yes, finding gas giants orbiting much closer to their stars than Mercury is to the Sun, around about 1% of Sun-like stars, was a bombshell. It seems highly unlikely that such monsters could form so close to the infernal blaze of their stars. Because during the early phases of their existence, stars blow away a large part of the surrounding gases, with the full power of their solar wind and their ultraviolet radiation. In other words, while most of the disk falls into the star, the rest is scattered farther away by thermal and magnetic winds. And near the star, there's little mass left to feed on, making it difficult for the forming planets to grow significantly. Therefore, if these giants of burning gas couldn't have formed so close to their stars, the question arises as to how they got here. The explanation that is now mostly accepted is that these giant planets were born, like Jupiter or Saturn, at a good distance from their star, where the more favorable conditions allow them to grow quickly and accumulate gas, and that they later migrated toward the inner part of their system, sweeping up and accumulating large amounts of material in the process. And the fact that giant planets are born beyond the ice line, can migrate, and over time transform into burning balls of gas, licked by the blazing fire of their star, also tells us a terrible story. Because you can imagine that when something heavy, like several hundred times our planet, migrates toward the inner part of a system, this can have dramatic consequences for all the other worlds orbiting near the star, whose orbits will be deeply affected by the arrival of the giant. In this simulation, you can see the absolutely devastating and terrifying effects that migration toward the interior of its system can cause. A giant planet with a mass like Jupiter, about 320 times heavier than Earth. Every little dot you see being pushed away, then often disappearing in the wake of its arrival. From the giant is a body whose mass is about that of the Moon to Mars. Destabilized by the giant's progression, the orbits of these bodies become eccentric, and in doing so, they cross each other, making moments when the objects dangerously graze each other more frequent. And so, a large number of planets in the making are ejected from the system, while others collide when they don't plunge directly into the massive giant or even into the star. In the end, the giant of... Gas has, in its progression, practically cleared its entire system in 100,000 years, barely 100,000 years during which a third of the mass of bodies once between the giant planet and the star was ejected from the system. Another third collided with other bodies and merged to form small planets. And all the rest ended up pushed far away, evolving on eccentric and inclined orbits. In some cases, a giant migrating toward the interior of its system can even disrupt the paths of small bodies that stand in its way, and alter their orbits to the point of sending them crashing into the rocky planets which are still forming near the star. And by repeatedly crashing onto the cores of these emerging worlds, these bodies can cause the inner planets of the system to spiral down into the star. In short, beyond what we have to call a real carnage, the main idea to remember is this. The orbits of planets can drastically change over time, because in newly forming planetary systems, when the gas disk that helped maintain the stability of the whole dissipates, it almost inevitably sets off. A dynamic instability during which the planets, in search of a new balance, see their orbits cross, which can have terrible consequences. And it helps explain why we sometimes find planets that have taken on trajectories extremely far from their place of birth. It was thus realized that the vast majority of gas giants orbiting at a respectable distance from their star do not have nearly circular orbits like those of Saturn or Jupiter. Instead, their orbits are often highly elongated. That is to say, they have eccentric elliptical shapes, like that of the planet HR 5183b, whose trajectory around its star you can see here. Compared to that of the giant planets in our system, and the fact that we are discovering a large number of planets with elliptical orbits is not insignificant, because it tells us that in the past, things must have gone very wrong in those systems. Let me explain. To those who read between orbital lines, a giant gas planet with an elongated orbit stands out. It's proof that in the past, the system being studied was the victim of gravitational instabilities of incredible violence, and that at the beginning of its history, the planets there waged war against each other. So each elliptical orbit is in a way a stigma, a scar, the remnant of a violent history that tells us that here, hundreds of millions of years ago, planets crossed, influenced, and destabilized each other, until one of the protagonists of the drama gave in and ended up ejected into interstellar space or propelled into the star. It is believed that when several gas giants reside within the same system, they become truly unstable after a few 100,000 orbits around their star. Their ongoing gravitational pull creates a ballet that's both chaotic and complex, where the outer planets will see their orbits lose their compact and almost circular configuration to follow highly eccentric paths. In this simulation, you can see how two gas giants orbiting very close to each other can disturb one another, to the point that in just a few decades, due to being too close, one of the two planets is ejected from the system and drifts alone in space between the stars. These planets are called wanderers, and now I think that I need to show you how. The presence of an extra gas giant in a system can literally blow it apart. Sean Raymond, who helped me write this episode, uploaded a simulation where you can actually see, let's say, chaos being born. He even called it self-destruction of a planetary system. And you'll see, it's not for nothing. At the top left, you can see time passing by in millions of years. At the beginning of the simulation, we have a relatively stable configuration that looks pretty much like our young solar system. Near the star, rocky bodies gradually grow by colliding with each other. And farther out, there's a disk of much smaller bodies that are rich in water. Between the two, 3 gas giants were placed instead of 2, as is the case in the other system. And after just over 40 million years of gravitational balance, the 3 giant planets will suddenly cause the whole system to collapse into a violent phase of instability, during which in just a few thousand years, all the icy comets, as well as one of the gas giants, are expelled into interstellar space, while almost all the forming rocky planets are destroyed. Of the 11 massive bodies ranging from Mercury to Mars, that were present at the beginning, 10 ended up plunging into the star, and the last one was ejected into space. Obviously, every planetary system is unique, but otherwise a typical system. In it, having initially formed 3 Jupiter-type giants, will almost inevitably leave. It will enter an instability phase at its beginning, an instability phase during which one of the 3 giants, and 80% of the small bodies called planetesimals will be ejected from the system, while half of the remaining planetesimals will eventually collide with another planet. The other half will fall into the star. By detecting many of rogue planets, those planets that drift alone in space without any stars to cling to, we have even been able to estimate their number at about 10. A number of planets of all types of mass that on average see the fragile and tenuous gravitational bonds connecting them to their system break. So as I speak these words, several trillion worlds, having been ejected from their systems, are drifting through the interstellar space of our galaxy. So, when our telescopes detect the presence of a planet with an eccentric orbit in a star system, it means a dramatic cosmic billiard game occurred there. Gravitational wars, which, as impressive as they are nothing exceptional. It is estimated that at least 3/4 of systems with giant planets on eccentric orbits have undergone violent dynamic instabilities during their initial phase of existence. It's an absolutely dizzying result, as it suggests that many planetary systems we see are, in a sense, small cemeteries, where planets have been lost in their stars or launched into the cosmos. We can even have fun roughly calculating how many worlds with masses comparable to Earth's have been destroyed by these giants in our galaxy. And the result is absolutely staggering, knowing that it's estimated there are about 10 billion stars around which gas giants orbit in our Milky Way. And given that 75% of these giants have eccentric orbits that can only be explained by periods of significant instability, and about 75% of these instabilities are strong enough to destroy another planet in the system along the way. So, that means that on the scale of a galaxy like ours, at least 5 billion Earth-mass planets have been destroyed. Think about that the next time you look up at the sky. On the scale of cosmic time, that's equivalent to a rocky planet with a mass roughly comparable to Earth's being thrown into a star, about every 2 years in our galaxy. And now I imagine you're asking, just like I am, how is that possible? If these disturbances are so common, yet the orbits in the solar system are so nicely circular, why don't we see any scars or little marks? Did our system malfunction and by luck erase evidence of eccentric orbits? And extremely lucky, we somehow slipped through the cracks. Or did it remain surprisingly calm during the first millions of years of its history? All these questions are still far from being settled, but a body of evidence suggests that we are survivors. We have seen that in the vast majority of cases, when researchers simulate planetary systems, they almost invariably see a dynamic instability occur. An instability that leads to the destruction of a large number of rocky planets or the building blocks necessary for their formation. And in the end, it leaves the system with only one significant planet, a giant moving on a highly eccentric orbit. But you may have noticed this. The orbits of Jupiter and Saturn are almost perfectly circular. They deviate from a perfect circle by only a few percent. In fact, what these very slight deviations tell us is that we did go through a period of instability, but it was relatively mild. With the remaining planets, the ones we know, and that are therefore survivors, contact us on L. As strange as it may seem, the puzzling results of our numerical simulations show that for a system with several gas giants like ours to become stable and be filled with planets having nice circular orbits, It almost inevitably has to go through a turbulent and chaotic period, from which it can only emerge by getting rid of one of those giant planets. When we run simulations to try to reproduce the peculiarities of the orbits of the giant planets in the solar system, we find that during the growth of ice giants like Uranus and Neptune, several heavy worlds, about 5 to 15 times the mass of Earth, are ejected from the outer solar system. It's even possible that one of them is still out there, but with such an eccentric orbit that takes it so far from the Sun that we still haven't detected it. Some researchers actually suspect the existence of a hypothetical ninth planet within our solar system, which would be moving on a terribly elliptical orbit, to the point that it would take about 10,000 to 20,000 of our years to orbit our star. And this planet, which would have suffered from the instabilities between the gas giants, would still be tethered to the Sun, forced to drift in the distant reaches of space. And it would only come as close as 200 astronomical units to our star, which is the distance between the Sun and Neptune. Finally, there's one last thing that's very strange. In fact, when we compare the architecture of our system to that of others, what stands out is that there is no planet closer to the Sun than Mercury. Yet, nearly half of the other planetary systems we've discovered have a planet in that position. One or more planets of the super-Earth or mini-Neptune type, that is, planets heavier than ours and slightly less massive than Neptune. As if our system had been hollowed out near the Sun. Here, there are two ways to explain this peculiarity. The first is to say that, for various reasons, it's very common for stars like our Sun not to form planets in that area, and that something therefore prevented the formation of planets closer to the Sun. The second explanation is to say that there really did exist in the past of our system planets in the process of forming in this region, which could have grown large enough to become super-Earths. But all of them, without exception, were either ejected from the system or sent into the Sun. In that case, what this absence tells us what? It's not that no worlds formed, but that all were eliminated, and that the traces of the crime have been almost completely erased. In short, the discovery of all these strange new worlds, whether they evolve very close to their stars or have eccentric orbits, has forced us to rethink the way we view the history of planet formation. And this story, once viewed just decades ago as a well-oiled celestial clockwork, is now seen as a chaotic dynamic where each giant planet, based on its position and mass, can disrupt the gravitational battles shaping planetary systems. But one of the most important factors influencing the arrangement of these gears may actually be found in the birthplaces of these systems. Within the stellar nurseries, where the gas and dust from immense molecular clouds collapse, igniting stars and forming the planets that orbit them. Because in these turbulent environments, where nascent systems brush past each other, some giant stars with short lifespans can immediately seed nearby young systems with powerful stellar winds and explosions, spreading highly radioactive elements. Our solar system very likely found itself in such a situation shortly after its formation. In fact, we find in it a significant amount of atoms resulting from the decay of aluminum-26 and iron-60, elements produced during the explosion of massive stars, and which likely played a key role in distributing volatile elements in the disk, and thus in the initial distribution of the planets. And if you doubt the ability of these simple stardust particles to influence the fate of an entire planetary system, consider that it is estimated that the aluminum-26 atoms initially present in our solar system alone emitted during the first 2 million years of their existence as much heat as all the other radioactive elements in the system have released throughout its entire existence, enough to have absolutely enormous repercussions on the diversity of possible gear configurations. Anyway, I have to say, I really like the idea that this completely new vision has allowed us to better understand where we come from. It came to us by studying systems located dozens of light years away from us. In an upcoming episode, we will relive in detail the incredible story of the formation of our solar system. A story that proved far more chaotic and turbulent than we thought. And we will see that the apparent devastation caused by the movement of gas giants is sometimes the price to pay so that other planets can slip through the turbulence. Because while the presence of Jupiter may have been fatal to some forming worlds that have now disappeared, this planet has also protected us. Just like a shield would against a population of asteroids and comets that resulted from its formation. Between the builders, the destroyers, and the protectors of worlds, the line is as thin as the thread of an orbit. And with that, I'll hand it over to Sean, with whom I had the pleasure of working on writing this episode, to share with us an essential point that we often forget to consider when we look into the process of planet formation. Sean, thank you so much for your help in writing this episode. Before we wrap up, you wanted to share with us an essential point that we often forget to consider when we're interested in the process of planet formation. Can you tell us a bit more about it?
What I'd like to say is that the observations we have show us snapshots, brief glimpses of planetary systems. It's like seeing 0.2 seconds of a movie, but not the whole film. And it's not easy to understand what happened to get to that point. Even if we have some ideas about what happened at the beginning, and in our case, the beginning, that means having data on protoplanetary disks where planets form, as well as data on exoplanets. That is snapshots and other movies as well. Numerical modeling like those behind the animations you've seen helps us understand how dynamic planetary systems are. Our human lifespan is so short compared to the length of these planetary movies that we only see a small part. But now we understand a little bit more about all the action that's going on behind the scenes.